Please start.
Okay. Okay. So I'm just going to begin again by recalling some of the stuff we did last time. So sorry, I'm using my other tablet, so I'll have to take me a little while to get used to this. Okay. Okay, so very quickly, Daha, that's the main algebraic structure behind the Mcdonald polynomials. So we thought of it as sort of being three layers in some sense. So there's the finite Hecke algebra, that's T1, T2, Tn minus 1. So this is the finite Hecke algebra. Then there are the bunch of x's and the y's. So you can think of it as x1, x2, xn, for example, or as x mu, as mu varies over Zn. And this is what we call y lambda check. Again, lambda check varies over Zn. And we had various relations amongst these. There was also a central element Q. And the key thing here was the polynomial representation of the Daha. So polynomial representation, which is the following. So we fix Q and T power half, sort of generic non-zero complex numbers. And the vector space on which the Daha acts, the polynomial representation, is, you can think of it as the group algebra of Zn. So we call this C of x. So I'm going to dispense with the plus minus notation there. So C of x will just mean the span of all the x mu's as mu varies over Zn. And the action of the figure out how to go to the next one. Sorry. Yeah. So the action of the double affine Hecke algebra on this space is, so we said it's given by the following. We just have to figure out how Ti acts on this generating element 1. That's just given by t to the half. This is for all I equals 1 to n minus 1. The y's, y to the lambda check or y to the mu check acting on 1 is given by the following. It's t to the rho mu check times 1. Okay, so rho, remember, was the what we call the y vector, half the sum of the positive roots. So this is half of n minus 1 epsilon 1 plus n minus 3 epsilon 2 and so on, till the last coefficient, which is minus of n minus 1 epsilon n. So you take the inner product of this element of, so this is a rational, it's an element of Qn, if you wish, and you take the inner product of that with mu check. That's your power of t there. Okay, and so this is the action, and in some sense you induce the action. So this determines the action in the affine Hecke algebra portion, the Ta and the y's, and then the induced module is what's called the polynomial representation. You induce this trivial representation to the entire Daha. So the action of all the other elements. So what are the x lambdas? How do the x lambdas themselves act? Well, they act just by multiplication. So how does x lambda act on the monomial x mu? It just gives you x lambda plus mu.
Sorry, you also use q, right?
I'm sorry, what?
Before inducing, you use q as well? Action of q? Acts by q.
Say that again?
Q acts by q as well, right?
Q acts by q as well, yes.
Before inducing.
Okay, absolutely. On the entire module, yes, q times. So I mean, this q is the central element, and this q is the scalar we fixed. So x to the lambdas act like this. And how do the rest of the elements act? Well, you can sort of figure it out by, if you know the sort of the commutation relations, or how to move the ti's past the x's and so on. So for example, if you wanted to know how to make ti act on x mu in the polynomial representation, you'll think of it as just ti acting on x mu acting on the polynomial 1. And then you sort of need to know what the commutation relation is between the ti and the x mu in the Daha. And that had the form something like this. When you move the ti past the x, it becomes x si mu ti plus some additional terms. And so which I won't write down, acting on 1. And then you use that to figure out what the answer is. Okay. And we had explicit formulae for this action. So let me just recall what the explicit formula was, because I'm going to use it later on today. Explicitly, ti on x mu is t to the half x mu, okay, minus, so that is t to the minus half times t xi minus xi plus 1 by xi minus xi plus 1 times, this is the operator identity minus si. So it's maps x mu minus si. Okay, so this is the formula for the action of ti on the monomial x mu in the polynomial representation. Now, what we also had are the actions of the yi's, which are the what we call the Cherednik-Dunkel operators. So we call the yi's themselves are the following. Oops. So the Cherednik-Dunkel operators, y1 is determined as so g times tn minus 1 t1, and y2 was, you put one of the t's over to the other side, keep the rest where they are, and so on. So these were the Cherednik-Dunkel operators. I mean the y mu's in general, I guess. Okay, so let me recall the intertwiners, which is what we use to construct the non-symmetric Mcdonald polynomials. So what are these? Well, these were operators on Cx defined as follows. So there's, on the one hand, there's an intertwiner corresponding to that element pi of the affine value group. So this was tau pi check, and this is just the action of g check. Okay, so recall that g check was just sort of a replacement for the x's in some sense. And then there's the other operator, tau I check, which is ti plus an additional term, which looks like this, t to the minus half minus t to the half divided by 1 minus yi inverse yi plus 1. Okay, and this is for all the i's between 1 and minus 1. So these are the so these tau I checks, there's one for each ti in some sense, there's one corresponding to each ti, but it's sort of a you add this additional term to the ti there, and the tau pi checks are the g checks. And if you recall, so we made this point last time. So what is the g check really? So as I said, g is like a replacement for the x's, and g check is like x1. I don't know if I have this right. T1, T2, Tn minus 1. Tn minus 1. Okay, so g check is really this operator on the polynomial representation, and the observation we made last time is that these tau pi checks are the operators which sort of increase the degree by 1, because they this x1 term in front, when it acts on some polynomial homogeneous of some degree, the x1 multiplication by x1 sort of increases the degree there. the action of the TIs does not do anything to the degree. So we just saw the action of the TIs there. So let's go back. So we see what TIs do. They don't do anything to the degree at all, because the second term, it's sort of like a divided difference, x to the mu minus si mu divided by xi minus xi plus 1. That sort of reduces the degree by 1. And then you're multiplying out by this txi minus xi plus 1. Okay. So the TIs sort of act by preserving the degree. And these g checks, or the tau pi checks, are the ones which will increase the degree by 1. Okay, now I just wanted to say this to mention a point which I neglected to mention last time, which is that, so we said, I said the following, that these guys satisfy the braid relations. So in other words, the, tau I plus 1, tau I plus 1, tau I is the same as tau I plus 1, tau I plus 1, and so on. So in other words, you can actually define an operator called tau w check for any element of the finite while group. So this is well defined because the braid relations are satisfied by the taus. Okay. Now, however, the square, so it's not quite the, it doesn't satisfy the other relation, which is the squares. Instead, we actually know what the squares look like. Okay, so tau I check squared, however, is the following operator. So let me just use notation that Arun uses in his note. So this is the C operators. So C of minus alpha I check yt times C alpha I check yt. So these are both operators. What are these? Well, these sort of depend on, so the notation here is like, this depends only on the y's in some sense. Okay, so what are the c's? So c plus minus alpha I check yt is just a sort of operator which almost the kind of thing which came up in the intertwiner. So it's minus half y, then you put plus minus alpha I check divided by 1 minus y to the plus minus alpha I check. Okay, and y to the something alpha I check. So y to the alpha I check. So recall alpha I check is like epsilon I minus epsilon I plus 1. So this is yi plus 1 inverse. So that's what we're calling y alpha I check. Okay, so anyway, the exact form at the moment is probably not too illuminating. The key point is that this only depends on the y's. Okay, when you compute the square of tau I check. And why are these nice? Then, so the point is, recall that the non-symmetric Mcdonald polynomials are going to be the eigen functions for the action of the y's. Okay, so this operator, we sort of understand how it acts on the non-symmetric Mcdonald polynomials. So it just acts as a scalar. So this acts as some scalar on the non-symmetric Mcdonald's. Okay, since we sort of know that, after the fact maybe. But the other important thing is, therefore, one sort of can compute the tau I check inverses also. So if you want tau I check inverse from this formula, just put an inverse on both sides. It's essentially tau I. Yes, I'm multiplying both sides of this equation by a tau I inverse. So tau I inverse is really a tau I times the inverse of this operator, C minus alpha I check. So I'll just suppress the i's for the moment, times C alpha I inverse. Okay, but on the non-symmetric Mcdonald polynomials, therefore, tau I inverse and tau I check inverse and tau I check just differ by a constant. So this is an additional constant that you're going to incur when you act on a non-symmetric Mcdonald. Okay, so that's just something we'll come up later. Okay, now so the point, what is the most important thing about the intertwiners was the following rule, that they sort of have the best possible commutation relation with the y's. So if you compute tau w check, so I'm just going to take a more general w now. If we take w, so So I probably said this is a well-defined operator for any element of the finite while group. I actually should have said more. This is not just for any element of the finite while group. In fact, this is well-defined for any element of the affine while. I mean, the braid relations are also satisfied for with respect to the pi, not just with respect to the tau I and tau hs. So I sort of forgot the pi is there. So this is the full braid relations for the entire affine while group itself. Okay, so I have an intertwiner corresponding to each element of the affine while group. So the natural thing is, how do those intertwiners commute past these y's? And this was the reason for the usefulness of the intertwiners, that they have sort of this nicest possible commutation relation. And the commutation relation is the following: when you put the tau w past the y's, you just get y to the w of lambda check. Okay. Now, just a quick remark about this. So what exactly is w of lambda check mean here? So recall, w comes from the affine while group, and lambda check comes from the lattice Zn that we talked about. Right. So in what sense is so there is no obvious action that, I mean, one can think of here. Well, I guess maybe there is no linear action, at least. So what does this notation mean when you take an element of the affine while group and act it on an element of the lattice? So what we are actually doing here, what we mean is the following. So this should be familiar for those of you who've seen maybe affine Kac-Moody algebras and so on, and the while group as defined there. So what you do is you sort of take this Zn and sort of throw in an additional dimension. So I mean, when one sort of talks about affine Kac-Moody and so on, you actually throw in two additional dimensions, but all the action will really be inside this space. So what you do is consider Zn plus this additional element k. Look at this bigger lattice, and now there is an action of the affine while group on this bigger lattice. Okay, so what's the action? How does it act? Well, on k is like k is fixed by all elements of the affine while group, but elements from Zn, when they are acted upon by w, will actually give you elements which also involve k in general. Okay, so so let me first say how elements of how the translations act. So if we take a typical element t beta from the affine while group, how does that act on this element lambda check? Well, it's lambda check minus beta lambda check k. Okay, so this is the action of the translations, and elements of the finite while group act in the usual way. So if I take an element from the finite while group, that's just the usual element of Zn. It's just itself. Okay, so it's really the translations which sort of act by involving this additional dimension. So this is sort of the usual way in which one defines the affine while group on sort of the action on weights of level 0, as they're called. Okay, and so then what does this really mean? Because you're raising y to the power something where this guy is not an element of the lattice Zn, but in general an element of Zn plus Zk. Okay, so this is now going to be, it's going to involve both the original lattice and some multiple of k. Okay, so we have the following identification. So anytime you see this multiple of k there, you sort of think of it as you put the q in there. Okay, you think of this. So what this means is, if I had y alpha 1 check plus 2k, for example, I think of this as y alpha 1 check multiplied by q square, or maybe q to the minus 2. Okay, so that's what that's the convention there. Okay, so you think of this as, I mean, it's now like you're working in the group algebra of this sort of larger rank lattice, one rank larger, and q now is like that, it's that e to the minus k. It's the additional element of the group algebra. Okay, but we are going to put, of course, q, we have fixed it to be a constant complex number. So we make this convention. Okay, so this, it turns out that this is the commutation relation between the intertwiners and the y's. And the correct way of thinking about it really is to think of this affine while group action on this, one rank larger lattice. Okay, so now let's recall the definition of the non-symmetric Mcdonald polynomials. So Mcdonald. The non-symmetric version is defined as follows. We take, well, there's a normalization factor, t to the minus half length of v mu, or v mu inverse, the same thing, tau of u mu acting on 1. Okay, tau u mu check. Where, if you recall, what are these u mu's and v mu's? They were defined as follows. So you take the translation t mu in the affine while group, and you express it as a product u mu into v mu, where u mu is the minimal length representative in the corresponding coset. So what's u mu?
Sorry, once again here, mu is in Zn, not Z plus N.
Mu is in Zn, yes, in Gen, yes. So I can look at the corresponding translation. I write it as, so this is the minimal coset representative, minimal length element in the coset T mu Sn, the coset of the finite while group inside the affine while group. And v mu is, well, once you figure out what u mu is, it determines v mu uniquely, has an alternate description. It's the minimal length element of Sn which sorts mu in ascending order. So such that v mu of mu is just mu sorted in ascending order. So this is the anti-dominant element of its while group order. Okay, so those were the definitions of the u mu's and the v mu's. And the key property here, so which I didn't derive last time, but let me do it now, which is these are eigenfunctions for the action of the y's. Okay? So the question is, y is, let's go a bit below. So if I take y to the lambda check acting on e mu, so why are the e mu's eigenfunctions for the actions of y's? Well, let's write this as, let's do this computation. So this we said is tau u mu check acting on 1 up to some scalar, which anyway doesn't affect this computation. So anyway, it's t to the minus half length of v mu. Okay, now I have a y and a tau, and we've just seen that they have this nice commutation relation. So I put the tau over to the other side, tau u mu check, and then this becomes, I guess, y u mu inverse of lambda check. Okay, I mean, the earlier relation was written in the other order, tau first and y next. So here I'm applying it in reverse. So it's this acting on 1. Okay, and now we just said, what does it mean? I have to figure out what this means with that additional k in place. So what's u mu inverse of lambda check? So this by definition, so I recall what u mu was. It was t mu v mu inverse. So I now rewrite u mu inverse back in terms of v's and t's. So it's this acting on lambda check. And if you sort of use that formula that we just wrote out, this is lambda check plus lambda check mu times q. Okay, and now, so therefore, what is y to the, y raised to this this element. So I need to raise y to this element. And as we just said, when you raise y to the k, that gives rise to the q factor. Okay, so the y raised to this whole thing, u mu inverse lambda check, is just y raised to the first term, which is v mu of lambda check, times the second factor, which is q to the minus q to the minus lambda check v. Sorry, this is only for the first. Yeah. So q to the minus lambda check v, okay, times. Okay, and so that's the so the eigenvalue is now the following. So how does, so I've gotten a q factor, and how does y act on 1? That we already said. That's the thing where you get the row in front. So let's write that out also. So this is therefore, so eigenvalue therefore is, so what we have finally computed is the eigenvalue for the action. It's the following. It's t raised to the row v mu lambda check and q raised to the minus lambda check. Okay, so this is eigenvalue when you try to make y lambda check act on e mu. This is, it's going to give you this multiple of e mu. Okay, so that's the so the proof itself is just the commutation relation between the intertwiner and the y's. Okay, now let's just write this in slightly different notation. It's called the specialization of the evaluation map. So okay, so the one of the things one does in this business seems to be the following, that so we sort of need to keep track of two different powers, one of t and one of q. And so here's a little artifice which makes it slightly simpler, which is let's just keep track of one base instead of two different guys. Okay, so let's think of t as again some power of q. So we'll put that exponent as small k here. So think of t as some q to the k. So I'm replacing the variable t really by this parameter k here.
So k is like a variable here, is it?
I'm sorry, what?
K is like some kind of an indeterminate or something to keep track of.
I guess you can think of it as a complex number now, right? Because I guess q and t are all complex numbers.
Okay.
So in that sense, k is again a complex number, for instance.
One other quick sort of philosophical question. Are these t and q supposed to, in some sense, be philosophically similar or related to the q and t in, say, Arvind's lectures? Or?
I guess so. Yes, I think they are. Yeah, they are going to be the same finally.
Yes, okay.
Okay. So morally, I mean, one thing about the t and the q, maybe Arun can pitch in here. So I think q is sort of like the affine. I mean, q morally seems to be like the affine, you know, e to the minus delta or e to the minus k or whatever it is. It's the additional degree of freedom coming from when you go from the finite to the affine. The t seems to be sort of more like a genuine parameter here, the Hecke algebra parameter. Arun, is that a reasonable description of?
Yes, yes, I think so. Yes.
Okay. So okay, so we replace t by q to the k. That allows you to sort of think of this in one unified fashion. You can just say this is you know, q to the k row. Sorry, what is my variable here? It's my mu. So I think of it as, so I push the v mu over to the other side. Think of it as v mu inverse rho. Okay, so here's, I'm just going to write a final expression here. So I want lambda check on one side. So it's q to the lambda check evaluated on k v mu inverse rho minus mu. Okay, so we just written the same thing, all to the power of q, but of course that k, remember, secretly means that there's, you should think of that as the what's going to give rise to the t term. Okay, and this is it's called the evaluation map. So what you're doing is you're evaluating or taking inner product or specializing at this element k v mu inverse rho minus mu of this lambda check or y to the lambda check. Okay, so this is the definition of the evaluation map. So what is the evaluation map really? If it's a map, so let me write this out properly. So you can, I mean, this is just another way of saying this is how we keep track of the eigenvalues. So if I take Cy, these are the Cherednik-Dunkel operators, there's an evaluation map at, I don't know what to call it, gamma maybe. Evaluation at gamma is the following. If I have y to the lambda check, then I just map it to q raised to the gamma lambda check.
Your gamma is an element of the Zn.
Right. So now yeah, I'm sort of deliberately not saying anything about that. Gamma is, I mean, gamma is going to involve this k here, for example. Right?
That's true.
So we sort of allow this slightly more general gammas. They're not just going to come from Zn. Gammas can be elements of, I suppose, Zn and
Zn.
Yeah. So it's like it's coming from this one additional rank lattice or whatever it is. So I don't know, qk or zk. I'm not sure what's the correct thing to say. Okay. So this evaluation is finally going to give you some power of q. Okay. So some complex number. And what we are saying is these are the eigenvalues really. So what we are saying is that for the action on the E mu's, the eigenvalue is just given by that evaluation that I wrote out. So E mu is nothing but the evaluation at that particular element, k v mu inverse rho minus mu, okay, of lambda check, if you wish, or y to the lambda check. So you can of course figure out similarly for more general elements, what the evaluation will look like. Okay. Fine. So
sorry, qk times Zn, right? Because I mean, ultimately you still have some vector v mu inverse.
There is also k v mu.
After the qk, there should be Zn.
Qk.
Or basically k times qk.
Oh, you're right. Yeah. That does make sense. So there's Zn and then maybe another k Zn. Is that right? There, it's sort of two copies of Zn really. Yeah.
That's it. Yeah.
Correct. Exactly. Okay, so so we computed the eigenvalues so far. Now the natural question here is, so the fact that the non-symmetric Mcdonalds were eigenfunctions for the action of y really came from the fact that the tau checks and the y's had this nice commutation relation. So we could ask the following question. We defined the E mu's as this specific element. You take tau u mu check of ones, but of course taus make sense for all w's in the affine while group, right? So if I take w, an arbitrary element of the affine while group, I can still define such an element, these tau w check of ones. So why are we really only considering these guys? So for example, if you try to compute, these will also be eigenfunctions for the action of y, for example. I mean, they will have the same sort of relation. When y acts on this, it will give you some scalar multiple of this. Okay. So, well, why don't we sort of look at them? Well, the answer turns out to be because the others are all zero. So let's take the more general situation. So I'm just saying the following. Suppose I say instead of taking w to be the u mu's, I take a more general w. So suppose w looks like some u into v. Okay, so u is a minimal coset representative. So maybe I should write it like this: w, I don't know what to call it, w mod w finite. So w finite is my Sn. So when I use this notation, I just mean take the minimal coset representatives of the finite while group inside the affine while group. Okay, and suppose I put some v, which is not the identity, but some non-identity element of the finite while group. So then if you actually compute this tau w check on one, you'll get a 0. Okay, and why is that? Because, well, firstly, if you remember, it satisfies the braid relations, and so here we have length additivity. So this is to get a reduced expression for w, you will just have to write reduced expressions for u and v and sort of put them together. Therefore, the tau for w will look like tau u check, tau v check. Now, the claim is that the tau v checks. So well, I can, if you want, write it further as a product of finite tau checks, ik check, all these I1s and so on are all between 1 and n minus 1. Sorry. So the claim is, if you act any of these tau I checks on 1, you're just going to get a 0. Okay, so let's just quickly check this. So if I take a finite tau I, meaning I take I between 1 and n, and I act on 1, well, what's the answer? Well, we had the actual expression for this, t to the minus half minus t to the half over 1 minus yi inverse. Okay, so you attempt to act this on 1, and observe ti acting on 1 was by definition, so ti acting on 1 was just t to the half acting on 1. Now this other guy here, we know how the y's acted. So recall y's were just, they give you t to the rho if you wish. So I'll just write out the answer here. It's t to the minus half minus t to the half by 1 minus, this is t inverse. Okay, acting on 1. So now if you sort of simplify this, so this gives you t to the half into 1 minus t inverse. So it's t to the half minus t to the half. Okay, so that's a 0. So the intertwiners, the tau I checks have the following property that they kill the element 1, and therefore these other tau w checks are all 0. So tau w check of 1 is just going to give you a 0 if w, if you don't take w to be a minimal length coset representative. So in some sense, these are the only non-zero answers that one gets when one computes the, when you form these intertwiners and act them on 1.
Sorry, Viswanath, can I ask
Yes.
you a question?
Yes.
So, what if we write W in the other way? First, we act on by the affine part, and then we act by the finite part. This argument seems to rest on the fact that you are first acting by the tau i's, which generate the finite while group, right?
So if you write it in the other order, then
so then you're saying there's some non-trivial reason why it will become 0, but here it's easier to see. Is it?
Why should they commute? Why U and V commute, is it?
Yeah, no, they don't commute in general. See, so when you write it in the other order, so maybe think of it as follows. What we are saying is tau w check 1 is 0 unless w is a minimal length left coset representative of the finite value in the other. That's all we are saying. So if you write it in the other order, it won't be as easy to detect when certain things are minimal length left coset representatives. I mean, they'll be sort of off by this. Okay. Also notice I haven't quite said that these other guys are non-zero. I mean, that's one of the facts we stated, that if you actually take a minimal length left coset representative, then what you get is a non-zero polynomial. I mean, that was, in fact, said the coefficient of x to the mu is non-zero. But here all I'm saying is that the other guys. So to answer your question, if in fact you wrote it in the other order, that it will be, and if that element were not a minimal coset representative, then it will become 0, but maybe not as easy to see. Transparent to see as this.
Okay, thanks.
But it will always become 0 if it's not. Achha, well, because of this reason you're saying.
Because of this reason, yes.
Yeah. Okay.
Yeah. Okay. So so like I said, the other fact that I didn't mention is that, so this is a proposition which not going to prove, which is that if you did take these guys, tau u mu checks, then those will actually give you non-zero answers. So it's not 0. In fact, coefficient of x to the mu in E mu is 0. So I should say, in fact, coefficient x to the mu in this guy is exactly what we cancel out by this, by the prefactor that we put on the E mu. Okay, so therefore, in other words, the coefficient, this coefficient is 1 in the Mcdonald polynomial E mu. Okay, so so there's also a stronger triangularity statement, but we'll come to that later. Okay, so the point, maybe one way of thinking about this is that, so firstly, it's actually enough to look only at left coset representatives. They are the only ones which are going to give you non-zero answers. The other important observation is that, see, if you had a left coset a minimal length left coset representative, or U, for example, see, if U is a minimal length left coset representative of the finite while group, and you wrote U as, product SI1, SI2, SIK. Remember, some of the SIs can be pi's here. Okay, so this is, let's say, a reduced expression. Then, all these subwords from the right. So if you cut it off at any point, what you get will also be a minimal length left coset representative. So this, all these right subwords of U will also continue to be minimal length representatives, because if any of them could be somehow shortened, if in their coset you could find something smaller, then the same would apply to U as well. Okay, so in some sense, the fact that see, if you compute tau U check on 1, you're going to do it via a sequence of tau i's like this. So some of them could be pi, again, remember. But the point is, at every step, I mean, there's sort of a recursive nature to this, which is already there. That, I mean, this guy is a Mcdonald polynomial up to a scalar, up to a power of t. Okay, because SIK is actually a minimal left coset representative. So this is going to give you some Mcdonald polynomial equation. And if you cut it off at the next step, that's again corresponds to some other tau U dash, which is SIK minus 1 SIK, if you wish. So that's again a Mcdonald polynomial, and so on. So you're actually, I mean, there's a certain recursive nature to this definition. The Mcdonald polynomial that you're computing at every intermediate step, what you get is a Mcdonald polynomial, and you're acting some single tau I check to the previous one. Okay, so okay, so let me.
So this is saying that the Mcdonald polynomial, whether for a higher length element is represented in terms of those of lower length elements, right? That's what this recursion is saying.
You can get them from the earlier ones by acting tau i's. Yeah. So we are going to do a little bit of that now. So here's the natural thing. So let's look at the Mcdonald polynomials E gammas, where gammas are all, let me say, in a finite while orbit of some mu. Okay. So let's fix a mu here. So fix mu in Zn. So I mean, let's fix it to be one of the following, dominant or anti-dominant. So maybe I'll just fix it to be anti-dominant. So anti-dominant just means it's already sorted in increasing order, mu1 less than or equal to mu2 and so on. And I'll call its dominant conjugate as mu plus. So mu plus is just mu sorted in descending order. I mean, the first part of mu plus is, so this is mu plus 1 and so on. Okay, so let me fix a mu, and let's, for the moment, look at what are all the Mcdonald polynomials of the form E gamma, where gamma is a rearrangement of mu. Okay, you permute the elements of mu. Okay, now, so again, so how does one get, what's E gamma really? So to understand this, let's just recall the definition. E gamma is t to the minus half length of V gamma, tau U gamma check on 1. Okay, and gamma, recall, is some rearrangement of the mu's. So suppose the following happens. Suppose gamma has an inversion at the ith place. Okay, so the inversion, recall, means that a larger number, gamma I is larger than gamma I plus 1. So I have an inversion there. And so now the question is, how do I understand? So what is it that I want to do? Given this, I want to understand. Sorry. So let me pose. So I want to ask, okay, if I knew this, then how do I figure out SI gamma from here? Okay, from E gamma, I want to relate them someday. So how do I get E SI gamma? Well, by the same sort of thing, right? It's t to the minus half length of, I need to figure out what is V for SI gamma. And then I have to figure out what is U for SI gamma. Right? So if I figure out how the U's and the V's change when I go from gamma to SI gamma, then I can try and compute E SI gamma from there. Okay, so how does V change? Well, so what was V? If you recall, V was the shortest element which sorts gamma in ascending order. Okay, so how do I? So this is the. So V gamma is the shortest element which does this. V gamma, when it acts on gamma, should give me my sorted thing, which is mu. Okay, same thing for SI gamma. So how do I sort? So observe, gamma has an inversion. So I first need to fix this. So how do you sort? How do you find the minimal V which does the job? You sort of do a greedy sort, in the sense you look for all inversions. I mean, inversion is adjacent inversions, and you set them right in any order. Okay, so you just pick an inversion, you set it right, then move on to the next inversion, and so on. So here, this process will always produce a minimal length element. So how do I fix gamma in ascending order? Well, I first fix this ith guy. Let me first apply SI, so that gamma I and gamma I plus 1 will be in the right order. Okay, having done that, I will proceed to fix the remaining elements, the remaining inversions. So in other words, I have to compute V for what's left, which is SI gamma. Okay, so V gamma is actually, and this is a reduced expression. Okay, in other words, to sort gamma takes one extra simple reflection, which is SI. Okay, so the length of V gamma is one more. So length of V SI gamma is one less. Okay, and further we also said this V of gamma is just V SI gamma into SI. Okay. Now let's figure out what the U looks like. So we sort of know something about the V now. So that's it tells you something about the power of t in front. Let's fix the U next. So how do you find the U? U, recall, is just T gamma V gamma inverse. So you have to put the V gamma on the other side. So now we sort of know how the V's are related. Sorry, still not figured out how to do this. Okay, so I know how the V's are related. It's also easy to see how the T's are related. So T of SI gamma will just be SI T gamma SI inverse, which is SI. Okay, so I know how the V's and the T's are related. From that, I can figure out how the U's are related. Okay, turns out U of SI gamma, if you just use this relation, it's going to give you an SI in front. Okay, let me see if I did that. U SI of. Okay, this is just a simple computation. Okay, and further, so the V here has V of SI gamma is length one less. Turns out U of SI gamma is actually length one more. Okay, and further, U is now longer. Okay, so V is shorter and U is longer. And why is that? Well, that gives me a chance to set right something which I sort of said wrong last time, which is the length of T gamma. So why is this? The length of T gamma stays the same. So length of T gamma, so is a formula which Arun mentioned last time, which is a translation, has the following length. So you just take all the positive roots of the type A diagram, which is I minus j, and you just look at gamma I minus gamma j. So the length of the translation T gamma is actually gamma evaluated on epsilon I minus epsilon j, modulus of that overall I less than j. Think of it as this. Okay, over all the positive co-roots, modulus. And I mean, the modulus says that it's invariant under permutation. So whether I have gamma or any rearrangement of gamma, any SN permutation of gamma, the length remains the same. Okay, so T continues to have the same length. SI gamma and T gamma have the same length. V has length 1 smaller, and therefore U must have length 1 larger. Because remember, we had length additivity here when you write it as U into V. Okay, so that's so this is the important thing, that you get U for SI gamma by taking U gamma and putting an additional SI to the left of it. Okay, now what does that imply in terms of the taus? It says that if you try to act tau of this element U SI gamma, right? Remember, that's what you need to compute the Mcdonald polynomial. The tau here, therefore, is just the following. You apply tau of SI, that's you put one additional tau I to the left of tau of U gamma j. Okay, just from what we said. This is a reduced expression with length 1 more. So when I act it on 1, it's really this. Okay, and so this is the sort of thing I was mentioning, that there is a certain recursive element to the definition. So what we conclude, therefore, is that tau I check of E gamma, not quite E gamma, there is still some power of T which I have to fix here. But so what is this element here? Is almost E gamma. Okay, so this is E gamma into T to the half length of V gamma. That's the normalization factor which I should correct for. Now what's the left hand side? That's again almost E SI gamma, except I need to correct for its normalization factor, which is T to the plus half length of V. Okay, so now we are ready to make our conclusion. So if you look at these two, therefore the conclusion is, how do you get SI gamma from gamma? So remember, the V's decreased in length, right? When I go from V gamma to SI gamma, the V goes down in length by 1. So there is one additional T power half on the right hand side after cancellation, and there is a tau I check E gamma. Okay, so this is if, remember, all this was under the assumption that there was a inversion at the ith place. So this is sort of a this is a recursive thing maybe. I mean, this is one way of getting the Mcdonald polynomial for SI gamma from gamma, provided gamma has an inversion at the ith place. Okay, so what is that? So any questions on any of this?
So this means that it's highly non-trivial that different ways of getting a particular E sub let's say gamma prime is you can get it in many ways starting from the identity, and all of them give the same thing, right? So that's a non-trivial check, or is it obvious from the axioms?
No, I think that's the braid relations of the tau I checks, right? And the fact that the tau I checks, I mean, I guess that's a non-trivial statement.
Okay.
Tau I checks satisfy the braid relation. So no matter which order you get to the gamma, you still get the same answer. Okay, so what does this mean? Well, this sort of says, how would you generate all the E gammas corresponding to, so recall, what did I start with? I started with an anti-dominant mu. So what it says is you can sort of fix every inversion. Every time you see an inversion, you can fix it and you will get the subsequent Mcdonald polynomial from the previous one by applying that corresponding tau I check. So in particular, it says I could, I could start with the dominant guy. So what's maybe the natural thing to do you would start with the dominant E gamma. So let's look at E mu plus. So observe mu. So what is mu plus? The dominant, right? It's got things in decreasing order. So I mean, everything is an inversion really. And of course, every element of, I mean, sort of the entire while orbit. So okay, mu is the anti-dominant guy, this is the bottom. So all elements in the while orbit of mu can all be obtained via a sequence of, I mean, you can keep fixing various inversions, right? You can apply a set of while group elements. So let's say I do SI1, SI2. So I can take the minimal sequence. So I keep fixing the inversions. Every time I see an inversion in, mu plus, or which will take me to a given gamma. Right? Or I can similarly do it to the anti-dominant guy also. So suppose SI1, SI2, SIK of mu plus is gamma. And let's say this is a reduced expression. Right? I take the minimal number of inversions which will get me from mu plus to gamma. Then what it says is that E gamma is just, how do I get it from E of mu plus? Well, I keep applying the corresponding tau I. I apply tau ik times a t power half. So it's a t power half tau I, which I need to act at each time. So this is going to give me, so if this element, I call it something sigma, you call this sigma, and what we have just shown is that how do you get E gamma from E mu plus? You act the corresponding tau sub sigma. So tau sigma is, remember, just tau I1, tau I2, tau ik. So if you have the dominant E mu, the Mcdonald polynomial corresponding to the dominant by mu plus, you can get all the other guys in the while orbit, all the other E gammas, by applying a suitable tau, the tau sigma, where sigma is now an element of finite value.
You want checks, right?
So check, yes. Thank you. Okay, and well, analogously, if you wish to get it from the anti-dominant guy, so observe then that just involves applying tau I check inverses. So how did we get this? So recall this equation, you can sort of read it in reverse if you want. Think of it as if gamma I is greater than gamma I plus 1, replace, okay, so I can think of it as follows. I run it in reverse, it's t to the minus half tau I check inverse acting on ESI gamma. And recall what I said at the very beginning, tau I check inverse is actually the same as tau I check, except for a constant in front when you act on a Mcdonald polynomial. Okay, tau I check inverse was tau I check times those C operators, the inverse of some couple of C operators multiplied together. But those C operators only involve Y's, therefore they act as a certain scalar on a Mcdonald polynomial. So this is almost like acting by t to the minus half, again by a tau I check itself, but there are some constants, some constants which are going to come up times ESI gamma. Okay, so the moral of the story really is that if you sort of start either with the dominant guy or with the anti-dominant guy, either by acting by sequence of tau I checks or tau I check inverses, as the case may be, you can generate all the other fellows in that while order. Okay, now, so let's just quickly do an example. So you recall this box greedy thing that we had right in the beginning. So if I take mu to be 0, 1, 2, that's an increasing order, then how do I get, sorry. So sorry, I'm supposed to start at zeros. Okay, so let me dispense with the. So if I have 0, so how do I reach? So recall, how does one write the reduced expression which gets you to 0, 1, 2? So you keep acting by pi's or si's. So if I do pi, I get 1, 0, 0. So cyclic shift and add 1. Then I do an S1. So you're allowed to perform any SI which sets right an inversion. So here 1, 0 is an inversion. So I need to set that right. And doing that will increase the length. That's the point. So 0, 1, 0. I perform S2, which gives me 0, 0, 1. Okay, and I perform another pi. I get 2, 0, 0. I do S1, I get 0 to 0. I perform, sorry, pi. Is it right? Sorry, what am I trying to do? I'm trying to get 0 to 0. So I perform pi. It gives me 1, 0, 2. And again, I perform S1, gives me 0, 1, 2. So this was sort of the box greedy, as we called it, reduce word, which gives me, so that's U of 0, 1, 2, which U of mu is this long word, which is pi followed by S1, S2, pi, S1, pi, S1. Okay, so that's my word, U0, 1, 2. Of course, let's also take the dominant guy. So if you take mu plus, which is 2, 1, 0 in this case. Okay, so I mean, as we have just seen, it's of course possible to get to the dominant Mcdonald polynomial from this anti-dominant guy by applying a sequence of SIs and applying the corresponding tau h checks. But let's just try to find a word which gets me to 2, 1, 0. So here I apply pi, I'll get 1, 0, 0. I apply pi again, so I get 1, 1, 0. Okay, now we apply, so here's an inversion. So we apply S2 at 1, 0, 1. You apply pi again and you get 2, 1, 0. Okay, so observe it's shorter. You get there quicker as you would expect, because as we've just seen, the dominant guy is the one which you'll reach first in some sense. And then from there you reach the other elements of the bilogical. You know, they take more simple reflections. So for example, here is another way, a different way of getting to the anti-dominant guy from this. So from 2, 1, 0, you can, you could have, if I wanted to get this, it's not the box greedy word, but here's another word which will do it for you. You first apply S1 because there is inversion there. I would have gotten 1, 2, 0. I apply S2, set this right, I get 1, 0, 2. And let's see, I apply S1 again, I would have gotten 0, 1, 2. So here's another word different from the box greedy, but this sort of tells you how those two Mcdonald polynomials are related. So if you figure out what is the Mcdonald polynomial corresponding to E 2, 1, 0, the dominant guy, then you just have to act this corresponding sequence of taus, which is tau 1 check, tau 2 check, tau 1 check. Right? That will get you from 2, 1, 0 to 0, 1, 2, for example. Okay.
And S1, S2, S1 is indeed the longest element in that finite.
Yes, S1, S2, S1 is indeed the longest element. Yes, absolutely. Okay, so so this seems to be a recurring joke almost now, I think. So I was supposed to get to the symmetric Mcdonald polynomials again towards the end, but maybe I'm already out of time. So let me stop here and continue next time. Venkatesh, is it fine?
Yeah, that is fine.
So it's turning out to be one of those dystopian lecture series where 90% of each lecture is a recall of the previous. Okay, yeah. So next time I'll sort of use this to define the symmetric, say a little bit more about the symmetric Mcdonald. So those will just turn out to involve these, all of these guys in some sense. So once we understand how all of them arise, then we can compute the symmetric Mcdonald. Okay, I'll stop here for now.
Any questions or comments?
Yeah, I have one question. Actually, sir, when we are going to construct anti-dominant element inside that orbit, then we'll start with finding the non-inversions at first, right? Then we'll apply S1, SIS rather.
Sorry, I didn't quite understand your question.
Okay, so when we are trying to find some Mcdonald polynomial lying in an orbit of some dominant weight, then we look for an inversion and apply tau I checks according to the reduced expression what we get. And if we start with from anti-dominant weight, then shall we have to seek for non-inversions?
Yes. You would then look for the non-inversions, but then remember you have to apply tau I check inverses in the other order.
Yeah, exactly. Yeah.
Can you explain why the braid relations imply that tau W check is well defined for all W?
No, because any W, see, how do you define tau W check? You say take a reduced expression for W, and then you write the corresponding tau I checks, right? You write W as SI1, SI2, SIK, and then you define tau W to be tau I1, tau I2, tau IK, right? So the general statement is that any two reduced expressions differ. I mean, you can get one from the other purely by using the braid relations, without ever using the square is identity relation. So therefore, the same, because the tau satisfy the same property, if you write a different reduced expression for W and write the corresponding sequence of taus, they will finally turn out to be the same operator.
Yeah, that statement actually, I thought it was true for Coxeter groups that like any two reduced expressions, you can go from one to other by braid relations.
Yes, that's all. We are only using the Coxeter group statement. See, what
Here we are working with extended affine, right?
Sorry, what?
So here W is...
You're asking the same thing about the extended affine value. That's a good thought. So I guess the tau pi's are also involved in some sense. So here by the braid relations, I suppose what you mean are the corresponding relations with the pi's also. See, pi SI, pi inverse is SI plus 1, so right? So these are, I mean, you sort of think of these also as being part of your braid relations. So maybe Arun can, is this true that any two reduced expressions in the extended affine, or what you're calling the affine value, are related by these braid relations?
Yes, yes. These are exactly the additional relations to add, yeah.
This is one of the problem in Raghavan's problem sheet.
Ah, wonderful. Okay, good. Nice.
Yeah, but you define tau of W where W is coming from the affine wheel group only for this lecture, right?
Yes. Hey, but affine while group is actually, I mean, what we are calling affine group is actually extended affine value. See, it's Zn semi-direct product Sn is what we are. It's what we would probably call the extended affine while group in the usual sense. So this is the affine while group of GLN. So this is Arun's notation for this. So this by itself is not a Coxeter group. It's not a, see, there is an additional element pi in some sense, which you have to take care of at every step.
Yeah, then the well-definedness of tau of W isn't, is it clear? Is it trivial? Very?
No, that's what. So that's what I guess Aritra was asking. So if you, so the statement now becomes, if I take any two reduced expressions of an element of W, which now will involve pi's and pi inverses as well, also as pi's and pi inverses, you can get from one to the other by applying either the usual braid relations among the SIs or these additional braid relations which involve pi's. So I don't know how, it's probably not too hard to prove that, I suppose. So was this proved during the tutorial, Venkatesh?
No, we didn't reach there.
Oh, I see. Okay. Maybe something to try.
It's not difficult because you can use that relation to move all the pi's to the left and then use the usual braid relations and then move the pi's back.
Okay. Yeah. Okay. Something that we should certainly try, I think, during the tutorial.
Just for the record, you should also put in the way length was defined. Pi inverse is equal to I. That's what's required formally, because.
I see. Right. Okay. That's in some sense an additional relation. Correct.
Pi inverse is also a reduced expression for identity by definition, because the lengths are.
Correct. So here, I mean, when you say a reduced expression, so these are all reduced expressions for the identity, right? anything with an equal number of pi's and pi inverses would count as a reduced expression.
The way it's defined, yes.
Okay.
Any more questions or comments?
Yeah, I just have one clarification. As Arun said that at first we will try.
I think I lost.
Yeah, I guess.
You have some kind of pi. S0 is on the left, then how it's stuck there,
Uh,
and or some relations, something like pi of. Sorry.
We sort of lost you in the middle. Didn't quite hear what. Could you just repeat your question again?